nobody's done it before. And it really took a tremendous amount of effort within Tesla engineering to figure out how do we make a freaking tabless cell and have it actually work and then connect that to the top cap. And it's there's a whole bunch of things that we're keeping a little secret sauce here that we're not telling everything.
If you care about electric cars, you've probably heard the phrase solid-state battery tossed around like it's some kind of magic key. Higher range, faster charging, safer packs, lower weight, fewer rare materials. It almost sounds too good to be true. Today we're unpacking what solid-state batteries actually are, why they could change the EV landscape, who's closest to making them real, and the honest roadblocks between the hype and your driveway. By the end, you'll know what's signal and what's noise, and when these gains might actually land in cars you can buy. Let's start with a quick primer. Most EVs today use lithium-ion batteries with a liquid electrolyte that shuttles lithium ions between a cathode and a graphite-based anode. Solid-state batteries replace that flammable liquid with a solid electrolyte, and many designs swap the graphite anode for lithium metal. That single swap is why people get excited. Lithium metal can pack more energy per kilogram, which means more range for the same weight, or the same range with a lighter, cheaper pack. A solid electrolyte can also be far less flammable than typical liquids, improving safety and potentially enabling tighter packaging and higher volumetric energy density. In theory, that adds up to cars that drive farther, charge faster, and last longer. In practice, it adds up to a massive materials and manufacturing challenge that the entire industry is racing to solve. What would revolutionary feel like behind the wheel? Imagine a family crossover doing 500 to 600 miles on a charge under favorable conditions, then grabbing 10 to 80% in about 15 minutes, reliably, for years. That is the dream scenario most solid-state roadmaps point toward. Companies pursuing lithium metal with solid electrolytes have demonstrated lab cells that hit 10 to 80% in roughly 15 minutes while maintaining strong cycle life. QuantumScape, for example, has shared targets and early data for a cell architecture designed around a ceramic separator and a lithium metal anode, highlighting sub-15-minute fast charging from 10 to 80% and pack-level energy densities that push well beyond today's mainstream lithium-ion. The caveat is scale. Getting that performance from small test cells to large automotive-grade multi-layer cells at high volume is the mountain to climb. Toyota has been one of the loudest voices around all solid-state batteries, and its recent moves are concrete. The company teamed up with Idemitsu Kosan, Japan's second-largest oil refiner, to mass-produce sulfide solid-state electrolytes, a promising class of materials for solid-state EV cells. Idemitsu is investing in a lithium sulfide plant slated to support tens of thousands of EVs per year, targeting completion by mid-2027, with pilot production planned earlier. That's not a concept, it's a supply chain commitment. If Toyota can pair those electrolytes with stable, high-energy cells at scale, we could see early solid-state introductions late this decade. Timelines can slip, but the fact that a materials supplier is standing up capacity and aiming to bring solid electrolyte costs down to parity with today's lithium-ion is a big deal. Nissan is also leaning in. The company has publicly targeted launching an EV with in-house developed all-solid-state batteries by fiscal year 2028 and has showcased pilot and prototype efforts to get there. Nissan's pitch is straightforward. If solid-state cells deliver high energy density with faster charge acceptance and better cold weather behavior, they can enable smaller, cheaper packs for mainstream cars and high power packs for performance models. Nissan has even floated cost targets like $75 per kilowatt hour around that timeframe, which would be transformative for affordable EVs. Though hitting both performance and cost targets simultaneously is the challenge every program faces. On the startup front, you'll hear two names a lot: QuantumScape and Solid Power. QuantumScape has published investor materials describing a first product sometimes referred to as QSE5 with energy densities above 800 watt-hours per liter and sub-15-minute charging from 10 to 80% while maintaining strong cycle life. QuantumScape's ceramic separator is designed to block lithium dendrites while allowing fast ion flow, a core tension in lithium metal designs. Meanwhile, Solid Power is taking a materials-first approach, scaling production of sulfide solid electrolyte powder and partnering with OEMs to integrate large-format cells. In 2025, it secured up to $50 million from the U.S. Department of Energy to accelerate continuous electrolyte production, and BMW has already begun testing large-format solid power cells on a BMW i7 development vehicle on public roads. These are the kinds of milestones you want to see if you're tracking real progress, not just press releases. Why is everyone so obsessed with sulfide electrolytes, specifically? In solid-state batteries, there are several electrolyte families: oxides, polymers, and sulfides. Sulfides have very high ionic conductivity at room temperature and are relatively soft, which can help them conform to interfaces and reduce resistance. The flip side is they can be chemically reactive and sensitive to moisture, producing hydrogen sulfide gas if mishandled, and they require carefully engineered interfaces to prevent degradation during cycling. Oxides can be more stable, but often need higher processing temperatures and may suffer from brittle interfaces. Polymers are flexible and easier to process, but usually need higher temperatures to reach the same conductivity as sulfides or oxides. This is the materials tug of war underneath the marketing headlines. Let's address the biggest technical villain: dendrites. These are tiny lithium filaments that can grow through an electrolyte during charging, potentially causing short circuits and capacity loss. In a liquid cell with graphite anodes, dendrites are managed by the SEI layer and charge protocols. In solid-state lithium metal cells, dendrites can pierce the solid electrolyte if the interface is imperfect or the current density is too high. Researchers and companies are attacking this from multiple angles: ceramic separators engineered to resist penetration, interlayers that distribute current uniformly, electrolyte formulations that suppress dendrite nucleation, and smarter charging profiles. A recent study reported a cohesion-inhibiting liquid electrolyte for lithium metal cells that tolerated aggressive fast charging in lab conditions, suggesting that careful interfacial chemistry can unlock both longevity and speed. While that result is not a drop-in car pack, it shows the physics can be bent in our favor. So what would solid-state actually change for drivers? Start with range. If you can move from a graphite anode to lithium metal and safely run higher voltages with a thin, robust solid separator, you unlock higher specific energy. Automakers can then choose their trade-off: keep the pack size constant and extend range, or keep the range constant and shrink the pack to lower cost and weight. Range anxiety disappears one of two ways: bigger batteries or better charging. Both are wins, if executed well. Next is charging speed. If dendrite formation is controlled and interfaces are stable, lithium metal cells can handle much higher current without the same degradation penalties. That means more power can flow during the critical 10 to 60 or 10 to 80% window of a road trip stop. The car side must be ready too: thermal management to keep cells in their sweet spot, power electronics that can accept high current without big losses, and a charging network capable of 350 kilowatts today and even higher in the future. But the heart is the cell. If the chemistry accepts the current, the rest of the system can be engineered around it. Safety is another pillar. Solid electrolytes are often non-flammable or far less flammable than conventional liquid electrolytes, reducing the risk of thermal runaway propagation. That does not mean solid-state packs are magically immune to all failures, but it does mean that event frequency and severity can be lower with the right materials and pack design. Improved abuse tolerance could open the door to tighter packaging and new structural approaches. If you're able to remove some of the heavy inert safety overhead that exists to manage liquid electrolyte risks, you can bring down pack mass and cost. That's a second-order benefit that matters a lot at the vehicle level. Cost is where dreams live or die. The industry's goal is to deliver the energy density and safety benefits of solid state at a cost that matches or undercuts today's lithium-ion. That's why Toyota's partner, Idemitsu Kosan, talks explicitly about driving down solid electrolyte costs to parity with current tech, and why Nissan has floated aggressive pack-level cost targets around its 2028 timeline. Early generations will almost certainly be premium. Over time, if electrolyte powder can be made continuously at scale, and interfaces can be processed in line, and yields can be kept high for multi-layer cells, you start to see the cost curve bend. It's not enough to make a great cell. You have to make millions of them, identical, cheaply, every week, for years. Where are we on the timeline? Between now and the end of the decade, expect two kinds of solid-state appearances. First, you'll see quasi-solid or hybrid approaches that use gel or semi-solid electrolytes to capture some of the safety and packing benefits without the full materials leap. Second, you'll see pilot and low-volume models showing genuine all-solid-state technology in limited production or high-end trims. SK On, for example, has pointed to commercialization of sulfide-based all-solid-state batteries around 2029 and has opened a pilot facility to accelerate that path. Traditional timelines slip in deep tech, but more and more of the milestones are now in manufacturing rather than just in the lab. That's the tell that the field is maturing. So when can you expect to buy a solid-state EV? Based on public roadmaps and tangible investments, late decade feels realistic for first-wave models from brands like Toyota and Nissan, with broader adoption into the early 2030s as supply chains stabilize and costs fall. SK On's target of commercialization around 2029 for sulfide all-solid-state batteries is a representative data point, and BMW's active on-road testing of large-format all-solid-state cells suggests premium integration trials are already underway. Here's my bottom line. Solid-state batteries are not science fiction. They're a very hard engineering project that is increasingly about factories, interfaces, and yields rather than whiteboards and theory. The prize is huge. For drivers, it's less waiting, more driving, and safer packs. For automakers, it's differentiation and the chance to reset the EV narrative with range and recharge times that feel simple rather than like a spreadsheet exercise. For the planet, it's a pathway to do more with less material and to make electrification compelling for the widest set of drivers. The next few years will be full of announcements, but the milestones that matter will sound like this. We've built electrolyte at scale. We've hit cycle life under fast charge conditions. We've validated